this video, I'm going to be talking about how to do math inside of an FPGA. Addition, subtraction, multiply, and divide. Not going to go into like trig or anything like that. We're going to do basic stuff here. And it's taken me a while to get to this video, and I'm surprised I haven't done it yet, so let's jump in. So first thing, a little bit of background that we need to learn is the difference between signed numbers and unsigned numbers. So how do you answer the question, is this number a positive number or a negative number? Is it 3 or negative 3? And the answer is, inside the FPGA, it actually uses something called 2's complement, which is a way to represent negative numbers. And I'm going to show a couple of examples, the difference between a signed number and an unsigned number, and how the FPGA interprets the numbers slightly differently, depending on how it's declared in VHDL or Verilog. So if this is a review for any of you, I do apologize. Quick review. It's going to be super fast. Stick with us. Okay. If I have something like 0, 0, 1, and I call it an unsigned number, that's equal to 1 in decimal. If I have 4 zeros, 0, 0, 0, 1. If I have something like 1, 0, 1, 0, and that's unsigned, this is equal to 10 in decimal, or A in hex. So far so good, everybody? What's 1, 1, 1, 1? 15 in decimal, right? That's true for any unsigned numbers. Now, if you want to represent a negative number, you have to use something called 2's complement. And the way 2's complement works is you take the number that you want and you invert the bits and add 1. So if I want to represent negative 6, then I take 6, invert the bits, this is 6, invert the bits, 1, 0, 0, 1, that's inverted, and then I add 1, 1, 0, 1, 0. So 6 in 2's complement form is actually 1, 0, 1, 0, which is what 10 or A was before. Okay? Trust me on this. Stick with it. Okay, that's what this is equal to negative 6. Pretty cool. If you want to convert back to 6, again, invert the bits and add 1. So 0, 1, 0, 1, and add 1 again, 0, 1, 1, 0. 6. Let's do another quick example. How about just 1, 1, 1, 1? What is that? If I say I have a signed number and it's equal to 1, 1, 1, 1, what is it in decimal? Well, invert the bits, 0, 0, 0, 0, and add 1, 0, 0, 0, 1. So it's equal to 1 in decimal. Okay, that's what 2's complement is. It's useful. It's how the FPGA deals with signed and unsigned numbers. It uses 2's complement inside of itself. It hides the inversion and the adding 1 thing. It hides all that from you. You don't need to worry about that, but I'm just telling you how the FPGA represents signed and unsigned numbers. One thing I want to make clear is that just because a number is signed doesn't mean that it can only be negative. Signed numbers can be positive and negative. The way you can tell if a signed number is positive is to look at the uppermost bit. If the uppermost bit of a signed number is a 1, it's negative. If the uppermost bit of a signed number is 0, it's positive. Let's look at this quick little chart here to show what that looks like. So I have a 3-bit number. Here are all the possible combinations of 3 bits, not maybe in the order that you're used to them. So 0, 1, 1 is the maximum signed value that's possible with 3 bits, 3. Unsigned it's just equal to 3 as well. So these two are the same. 0, 1, 0, 2, 2, those are the same. 0, 1, 1, those are the same. 0, 0, 0, 0 is the same for both signed and unsigned. Where it is different is for anything that has a 1 in the uppermost bit. That's where the numbers are different. You know, in an unsigned number, 1, 1, 1 is 7. With a signed number, it's equal to negative 1. If you do invert the bits and add 1, that whole thing. 6, 5, 4, negative 1, negative 2, negative 3, negative 4. So inherently, if you declare something as a 4-bit signed number, you're not going to have as much on the positive side as you do with an unsigned number because of the fact that your most positive number here it now has to be a negative number. You lose half of your range with a signed number. Back to the slides. Try to always use signed and unsigned types in Verilog and VHDL when you're doing math, I should say. So Verilog has reg signed 7 down to 0, factor 1, and VHDL has signal factor 1 of type signed 7 down to 0. Whenever you're doing math, always use signed or unsigned. It just makes things so much easier rather than trying to do just math on reg, because like, is it a signed number or an unsigned number? And you really should be able to answer that question. A signed number can be negative, an unsigned number cannot be negative. So can your input to your math equation be negative? If so, use signed. If not, use unsigned. There you go. One quick note here for people who use VHDL. In VHDL, you can use IEEE and then the package. This package right here, Standard Logic Arith, is used all the time, and it sounds great, but you should not use it. And the reason, quickly, is that Standard Logic Arith will allow you to do math on standard logic vectors, and numeric STD does not allow that. You should never be doing math on standard logic vectors. You should only be doing math in VHDL on things that are declared as signed or unsigned for the reasons I just said. An interesting little tidbit here, IEEE Standard Logic Arith is actually not an IEEE supported package. It's snuck in there, and it makes you think it is, but it's not even a good one. So don't even use it. Use numeric STD. It's much less likely to make errors, and it forces you to... It's a little more difficult to deal with, but it forces you to do the right thing, which is important. Adding. Adding is easy first place to start. How do we add inside of an FPGA? Well, in VHDL and Verilog, you can simply use the plus operator, and that will add two numbers together. One little side note, though, is that you need to make sure that you have enough bits for the answer. So, for example, what happens if in 1 is F and in 2 is 1? Well, we're going to get an overflow condition, and I'll demonstrate that. So quickly here, if you have like reg unsigned 3 down to 0, in 1 and 2 and out, then out can only ever be 4 bits. So out can be at most equal to 15. So if in 1 is equal to 10 and in 2 is equal to 10, guess what? Out is not going to be able to be equal to 20 in this scenario because it's only got 4 bits. That's going to be an overflow problem. That's not good. You want to avoid that. So what you do to fix that is just make out 1 bit wider than your inputs. And in this situation, I've made it a 5-bit vector, so now out can be anything from 0 to 31 decimal. All right, yeah, 31. And so if you have 10 plus 10 in this scenario, out can be stored in there, no problem. So as a rule, addition requires 1 extra bit, always for safety, to prevent overflow conditions. The one caveat to that rule is, unless you know for sure that your outputs are never going to saturate. So like, let's say you have 2 4-bit inputs, but you know that the inputs can only ever be 0 to 7 maximum, then you're okay with a 4-bit output because 7 plus 7 is still 14. That fits in 4 bits. Good to go. You need to make sure in FPGAs that when you're doing things, you have enough space for the result, because the FPGA won't know if you don't have enough space. So you need to be aware of what you're doing. So like, am I adding 2 4-bit numbers together that can go 0 to 15? Guess what? I need a 5-bit result. Am I adding 2 4-bit numbers that can go 0 to 7? I don't need a 5-bit result. I can use a 4-bit result. That's fine. You need to really know what you're doing, which can be tedious for people who are used to just the compiler taking care of all that stuff for you. So quick examples here. So if we have 2 4-bit numbers, you have, let's say, 0 0 1 0, and I want to add that to 1 0 0 0. Do the same addition that you do in, I don't know, 7, 6. When do you start learning how to add? 3rd grade? Yeah, sure. Okay, 0 1 0 1. Yay. Cool. Let's do another one. 1 1 1 1 plus 1 1 1 1. Okay. 1 plus 1 is 1, carry the 1. 1 plus 1 is 1 plus 1 is 0, but the other one is there. I'm sorry, this is a 0. Whoops, 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0, plus 1 is 1, carry the 1. 1, carry the 1. 1, carry the 1, 1. So here's a situation in which if this output wasn't declared to have 5 bits, you'd have an overflow problem. You would say that 15 plus 15 is equal to 1110. That's not right. That's not good. That's what? 14. So always make sure that you have an extra bit for your result. That's rule number 1. Let's move on. Subtraction. Subtraction, the same rule applies here, where the output should be 1 bit bigger, unless you know for sure you're never going to get an overflow condition. But it's 1 bit. Who cares? Just add it on. It's not a big deal. FPGAs have tons of registers. Using one more for an output is not going to kill you. I promise. And fun fact, adding and subtracting work exactly the same way. And the way they work the same way is this magic of 2's complement. 2's complement kind of takes care of all this stuff. You don't really need to know how addition and subtraction work. The synthesis tools will take care of all this stuff for you. Like exactly how it gets implemented inside the FPGA is up to the synthesis tools. And they're really good at it, and they'll take care of all this stuff. But I just want to show you quickly that 2's complement does, in fact, work, which is pretty cool. So the way subtraction works is the same as addition, but if you subtract a number, that's really like adding the negative number. So for example, if I have something like 3 minus 1, well, that's really 3 plus negative 1. Same thing. So if you can do addition, you can do subtraction. Sorry, if you can do addition of negative numbers, you can do subtraction. 2's complement allows you to represent numbers negatively, so you can do subtraction. Pretty cool. So let's do 3 minus 1. 3 minus 1. So 3 is 0, 0, 1, 1. 1 is 0, 0, 0, 1. But we need to represent it in 2's complement form in order to turn this into a plus. So again, go from regular number to 2's complement, we invert the bits and add 1. So this becomes a 1, 1, 1. This is a 0, add 1, it becomes a 1. So now this becomes plus. Okay? That's 3 minus 1. It looks weird, but that's what it is. Let's do some math. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0, plus 1 is 1. Carry the 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. This is our result. 1, 0, 0, 1, 0. Which I will tell you slyly, ignore this. This is your result right here. What's that? 2. Oh my goodness, 3 minus 1 is 2. It works. The reason why you can ignore this bit is because FPGAs are cool, and some smart people figured out that this is an overflow check, and if you want to really understand how that bit gets ignored, go read the Wikipedia article on 2's complement, because it explains it pretty well. And I don't really think most people care about the details of how this gets implemented inside the FPGA, but if you do, go check it out. Wikipedia, it's good. So one thing I want to highlight here is the results of adding and subtracting 2 numbers is the same. It's the interpretation that makes the difference. So the math works the same way, but whether or not the number is unsigned or signed, as a result, if the answer is unsigned or signed, that's the difference. So if the answer to anything, whatever it is 1, 1. What did we have before? 1, 0, 1, 0, and we say that's a signed number, the answer is -6. If the answer is 1, 0, 1, 0, and we say it's unsigned, the answer is 10. So you need to be very clear, is it signed or unsigned when you declare your variables, which is why I say always do that. Hopefully that makes sense. Again, a lot of these details are kind of abstracted away from you. Okay, multiplying. The rule for multiplication is the width of the result will be a maximum value of the width of factor 1 plus the width of factor 2. So if factor 1 is a 4-bit number and factor 2 is a 4-bit number, add them together. 4 plus 4 is 8. The output needs to be 8 bits wide. That's the maximum possible value. If you have a 2-bit times a 4-bit, the output needs to be 6 bits total. Pretty cool. Simple rule. Multiplication will likely be pushed into a DSP block. So DSP is digital signal processing block. I wonder why it's called that. It's a multiplication block. It does multiply and accumulate. It's usually used in DSP, which I guess is why it's called that. So those are specific tiles inside of an FPGA that are basically built for fast math operations. You can do multiply operations. You can do multiplies outside of a DSP block. It does use resources. The synthesis tools will generate interesting ways to do multiplication outside of a DSP block. The DSP blocks are just geared for doing multiplication like super fast. So if you have really fast multiplications that need to be done at like 250 megahertz, you need to be multiplying two numbers together on every single clock cycle of a 250 megahertz thing, and you got to do it 200 times in your FPGA, you probably want to be looking at some DSPs to do that. Or if you want to do some multiply accumulates where you multiply two numbers together and then add something else into them, that's another reason why you might want to use DSP. Those are like pretty common in filters and signal processing applications. So DSPs are good for that. If you're doing anything like that, read the user guide on how the DSPs work, because you're going to need to understand it pretty well. It's a little beyond the scope of this talk. Fun way to multiply and divide by 2 inside of an FPGA. If you ever need to multiply or divide by 2, simple way to do it, shift left for multiplication. Your left is this way. Shift right for division. So if I have a 4-bit number and I want to multiply it by 2, I can just do shift left by 1 bit, and that'll num1 now will be equal to 2 times what num was previously. And in VHDL, the way this works is, again, using numeric std package, a 4-bit unsigned number, call this shift left function, which is built into numeric std, num1 by 1. So that'll make num1 now it will be 2 times what it was previously. Shift right will make it smaller. Pretty cool. A lot of multiplication and division is done with the power of 2. And I would say, like, if someone in MATLAB tells you to divide by 1,000 or something, just be like, how about 1024? That's going to make my life way easier if I can multiply or divide by 1024. If someone really needs to do 1,000, then it's a lot less efficient. You can still do it, but multiplying and dividing by 2 is like lightning fast, super low resources. And I will say here, it's really not easy to divide by other numbers inside of an FPGA. Division is hard, and there are a few ways to solve this problem. There are some really complicated, and by complicated I mean like really resource-intensive division algorithms that can be implemented. You won't be able to do it on your own, but they're built into some of the synthesis tools. And if you really need like super fast division, you can try to look at some of those things, but they're really resource intensive. You can do slower division, so you can take a lot of clock cycles to figure it out. Basically, you divide something, you find a remainder, you divide the remainder by the new thing, find a new remainder. It's like this circular process, and I've written division applications like that before. And it just takes a lot of clock cycles to get your answer. But if you have a lot of clock cycles, then that's fine. So that might be an answer there as well. But in general, division is not easy to do. Not like addition, subtraction, and multiplication. Those are easy. Division is a little tough. So if you need to do specialized division, another way it could be like a lookup table. So if you have your input on your X and you have an output on your Y, you can just do a lookup to what the answer is going to be. I've used that sometimes. But yeah, division is not great. It's not the best. So, summary time. When adding and subtracting numbers, the output must have one more bit than the biggest input to prevent overflow. Good rule. When multiplying, the output must have as many bits as the number of bits in factor 1 plus the number of bits in factor 2. Otherwise, you'll get overflow there. Multiplying and dividing by 2 is easy, just using shift left and shift right. And dividing by anything else is hard, so try to avoid that. Hope that helps to answer some questions about multiplying and doing math and all sorts of fun stuff inside of an FPGA. If you haven't yet got yourself a Go board, please go buy one today. It's the best way for me to keep making these videos. Even if you got another development board sitting there on your desk, throw that one in the garbage. Go get yourself a Go board so I can keep making videos, and that'll be great. Thanks very much for your support. I appreciate it.